Good afternoon. Welcome to your second class for the preschool projects in Advanced Construction 4. Today we will be looking at the site, the location. We will look at the energy efficiency for the building. We identify a site where our climatic zone is situated and the energy usage in SANS 1004 XA. For the first part of our chapter for the class, we will be looking at the design occupancy of the building, the occupancy of the building itself, what code does it have. We will be looking at the building's orientation, and we will be looking at the walls and roof systems for the building so that we can do a retrofit of the building itself. We will slightly introduce into and talk about fenestration calculations and the energy demand on the electrical grid of a building. However, that is not required for our project and the task we have at hand. We'll only be focusing on the wall systems and the roofing systems. Okay, so SANS 10400 XA, the 2011 edition. There's two parts. There's part X, environmental sustainability, and part XA, energy usage in buildings. If we had to scroll down the building, if we had to scroll down the page, there's many focuses that one has to apply when applying 10400 XA. The actual reason for 10400 XA is we need to do energy calculations for the council itself. It's a requirement for plan approval for the council to know that you have applied the correct regulations to deem the building energy efficient. So there's sections and chapters on hot water supply, energy usage in the building envelope, the maximum energy demand for building classification, the climate, design assumptions, design population, design occupancy times. All these factors need to be taken into account. Orientation, roof assemblies, your climatic zone graph that indicates where in what climatic zone you will sit depending on your site. So 10400 XA is a basic summary of what you need to focus on when it comes to energy regulations. However, 10400 XA refers to SANS 204, which is a complete document overlooking energy efficiency in buildings. Okay, so just quickly go through the document. We'll be looking at the requirements of site orientation and building orientation, the importance of the north arrow graph that is indicated here in this figure, the building design, the energy demand within a building, and the annual consumption per building, our floors, our external walls, the CR values required for external walls depending on type of applications that you apply, construction techniques that you apply, if it's brick walls, if it's alternative forms of construction, what needs to happen. External non-masonry walls shall. That is what is required. And what we will be focusing on if we have non-masonry walls. Okay, fenestration, we'll go through as just a guide to talk to about fenestration, but it's not required in this class or for this project. Fenestration is a very comprehensive subject to speak about getting a building sufficient for energy. Okay, we will be focusing on roof assemblies, the climatic zones, and what minimum R values we require depending on the direction of the heat flow. What we actually require of an R value for a roof assembly. There are different types of roof assemblies with foil depending on the material that is chosen, if a roof is ventilated, if it's not ventilated, etc. The type of insulation that can be used to accommodate those R values in the climate zone, and what is the minimum thickness required for that installation board. Okay. The rest is part of energy consumption and how much electricity needs to be allocated and used. This depends on the amount of plugs and lights that are placed into a building to allow for how much energy is it to be drawn from a building itself. Okay, if we go directly down here to page 13, the first thing we'll look at is in our climatic zone, where do we sit? Okay, so let's go to our site. Alright, okay, so as we get to the north, we can see it is in the area close to university by Victoria Industrial, Laudium, Archibald, etc. So you as an individual need to understand if you are in this vicinity, close to two main metropolitans, where would your site in which climatic zone would it sit? For today's exercise, I will be doing all the calculations according to Johannesburg's climatic zone. That is where I am currently now sitting in Johannesburg. But for the site itself, you need to identify in what climatic zone the site sits. So here is a breakdown of the climatic zones of South Africa. I am in Johannesburg, so my climatic zone would be 1. You would have to identify where the site is and in what climatic zone do you sit. Another breakdown can help. The page after this document will be uploaded to my tutor for you to access so that you can have this document ready to look at all the information. Okay, so looking which area is closest necessary to the site, then you would understand where your climatic zone is. Okay. Let's go to the top. Now we will go look at, let's jump straight into building orientation, building design, and external walls. Okay, building design and orientation. We will take the project as it is true north. We will identify the building as true north. This is mostly relevant when it comes to the fenestration calculations because of the CR values and R values that is transmitted and the UV rays and things that are transmitted through fenestration. And through the calculations, you would actually know if you need to have double glazing, if you need low tinted windows, or if a standard 6.38 window will suffice with a steel frame, or an aluminum frame, or a timber frame. It is important to understand the orientation. We will assume that the building is exactly true north on 0, just to make it easier for the experiment. We won't be looking at the energy demand now. Okay, let's go directly to external walls. All right, we are external walls. External walls such as not limited to cavity, grouted cavity, I-frame, collar jointed, and single leaf masonry shall achieve a minimum CR value given in the table 3. Now, is it true if I say we will not be using masonry walls? So the table below and the typical CR values does not apply to what we want to do. This will apply if we were actually using a masonry wall. So for 0.3.3.2, external non-masonry walls shall achieve the CR values given in table 3 by addition of the capacity or resistance or both. Have the following R values except for climatic zones 1 to 6, for climatic zones 2 to 3 to 4. Right, so identifying this is I was in the climatic zone 1. So I'm in climatic zone 1. If you believe you are in climatic zone 1, or if you believe you're in another climatic zone, you need to remember what your associated number for your zone is. So I'm 1, so if we had to go back, okay, for climatic zones 1 and 6, a total R value of 2.2 is required. So I know my resistance of materials to whatever materials I apply needs to be a value of 2.2. If it's for zones 2 or 3, 4, and 5, then I need to have an R value of 1.9. How do we achieve an R value of 2.2? Different materials have a certain R value level. It is important for you to find out that the gypsum board that Marley supplies, what is its resistance value? It might be 0.31, it might be 2, it might be 1.5. I am not sure that it's the task for you to do, but this, the wall calculation, you need to get to 2.2. Okay. That is as simple as it is. What you require is I would want you to have a table and you have a breakdown of every single item that you use, what is the resistance, and what is the total amount of resistance that is allocated. If I had to give you a basic idea of insulation and type of insulation that can be used for resistance, let's go to here, for example. Okay, this is for a roof assembly. So you can't use this for the walls, this is for roof assembly, but it's just to give you an idea of what thicknesses can actually allocate to R values. So if I was at 2.2, a roof, there's much higher resistance that is required in a roof because it's directly hidden by the sun from above. Now, say for argument's sake, that was 2.2, and for me to have 2.2 to sufficiently insulate the wall, I would need a cellulose fiber loose fill of 135 millimeters thick, or a flexible mineral rock wool, which would give I'd need 115 millimeters to get that resistance value. Extruded polystyrene XPS, I would only need 100 millimeters thick XPS to give me an R value of 3.7. So you would need to go find out what R values or what thickness of insulation you would apply inside of your retrofitting wall to give you an R value of what you require for your climatic zone. So I'd like to introduce you guys to the class of occupancy of a building. Now, in the table that you see in front of your screen is we won't be covering energy demand and energy consumption for lighting in this class, but just to make yourself familiar that every single building has a different class that it's associated with. For example, where you stay in a dwelling house, your class is actually an H4, and an outdoor sport with a viewing is an A5, and a church or a mosque or whatever would be associated as an A4 class. Now, this is just to take into account for its importance when you do energy consumption, but also for the council to know before we do looking at the plans or, before they look at the plans and scrutinize the plans and look at the energy demand that you require for the building, they look at your class so that they are associated with what you are doing. Now, let us move on for what we've spoken about walls, take into account the class, and let's go and do a summary. So you can decide in what class you believe the project of a classroom, but also a place where someone stays, is associated to. Now, I am doing the task of using myself, where I currently stay in Johannesburg. So my class is, I'm an H4. What is important about this is the design occupancy is that the building is used for 24 hours a day, 7 days a week. There's always someone here, there's always activity happening in that space. That is the reason why the design occupancy becomes important to identify. Now, we look at the climatic zone. So what I'm basically doing is I'm giving you a summary of what we just discussed and what you need to jot down for what you need to do. I am in climatic zone 1, not 3, not 5. I've identified that Johannesburg is climatic zone 1, the Golden area. That's it over there. Okay. Let's go to orientation. Now, I'm starting to get a summary of everything that's happening so far. So my occupancy is H4. That's how much design occupancy that I use. This you don't necessarily have to show in your guys' work. This is just going to explain to you that every single different occupancy has different design occupancy times. I mean, climatic zone 1, I said for the argument of the project, we will make the orientation that is true north. Okay, we will go to the energy efficiency in buildings. I've identified with what I have here, my wall type. Is it masonry or is it non-masonry? It is non-masonry. If it is non-masonry, I need a minimum R value of 2.2 for my wall skin. Now, how do I get to 2.2? I apply different materials to what I need to do for the project. Take into account air, try and find out what resistance value air is. Try and find out what R value steel sheet has. I can tell you now, steel sheeting has a very low resistance, but it can benefit your 2.2 application. Air can also benefit your application because it helps determine how much resistance you can actually have if you had to place your materials right against the sheet metal for the existing building, or if you actually create a little bit of a gap to help with the resistance to apply less materials because even your air has a resistance value. All right, let's move to roof assemblies. Now, if we go to a roof assembly, we have to take into account the resistance is much higher than what a wall is. The roof is usually more exposed to the sun than what the wall is. So if you look at my screen, for where we have the roof assemblies in the Science 204, 4.3.6 roof assemblies. Table 8, what is the minimum total R values of roof assemblies? Remember, I'm in Kinetic Zone 1, so I have a minimum requirement of 3.7. I have a direction of heat flow up. Every single climatic zone has a different direction that the heat actually moves within a building, and this also needs to be taken into account. Now, let's move further. I know now I have 3.7 resistance I need to achieve. Okay, then thermal installation, this is a good read for you guys to read to understand things more effectively. But we won't be going into depth of this as we won't require it now. Okay, so for my 3.7 and a heat direction of heat flow that is up, one could actually put in a reflective foil laminate. That is side solution that can be applied to actually redirect the heat and it bounces away from the building. So it's like a very thin aluminium layer of foam that is applied to resist a lot of the heat that comes in. If I were to apply foil, what would be the recommendations or what would be the resistance that I would achieve? So my direction of heat flow is upwards. So I'm upwards. I don't have a ventilated roof. So I'm a non-ventilated roof. However, pitched roof with horizontal ceiling. I don't have a horizontal ceiling. We have a pitched roof with a cathedral ceiling. It's closer to 22 to 30 degrees in this area, and it's an upward flow. If I had to put in isolation, I can add it to my calculations. This is what resistance I would have gotten from isolation. However, I'm not applying isolation, so this was just for you to have extra information. Okay, so let's move to this area where let us find out what is the required insulation that I need for 3.7 in my climatic zone. My direction of heat flow is up. We know that. This is estimated total R value of roof assembly with materials of the roof covering and plasterboard. Estimated minimum R value of insulation. Okay, so this is my minimum insulation value that I need if I use insulation plus if I have this as roof covering and plaster. So 0.35, 335, that plus this will give me 3.7. Okay, so if I go now to my different insulation material types, if I wanted to apply EPS for 3.7, I need to use 100 millimeter thick EPS to have a resistance of 3.7. That is true if I have roof covering as well and plasterboard as a ceiling. So for 100, it gives me a resistance of 3.35, but including the other materials, because we're not just using the insulation board as our roof, we have multiple layers. I have a 3.35, and then that allows with the other materials to give me a certain resistance. What do I mean by this? Let's go do a summary again. All right. So here is a summary that is given for my roof. So remember my occupancy, my climatic zone. The required R value is 3.7. Direction of heat flow is up. Let's go to the construction, the base construction side R value. I will be using metal sheet type. And R value of the roof covering material is 0.35. The ceiling is 0.05, and the required R value for insulation is 3.35. Now, this includes the air gap, the roof sheeting itself, and the air gap layer that is underneath the roof sheeting. It gives me a resistance of 0.30. If I use a plasterboard ceiling, I get a resistance of 0.05, and then this is the minimum insulation R value that I need. Same as if I want a 3.35 resistance of insulation, I need to choose one of these in their thickness to allow for me to have a 3.3. Is my roof ventilated? It's unventilated. Let's do the basic construction of the roof. It will be metal cladding, pitch, cathedral, open beam. Okay, here's a basic breakdown of the resistance of materials. We all have an outdoor airfoam that sits on top of our roof sheeting or tiles or whatever. It's the same principle of when you drive a car on the highway. Everything, including your car, has a very thin air layer that sits over an object. It's the reason why, if you had to think of it, if you're driving down the highway, why does the dust not just brush off your car because of the air that's brushing against the bonnet or the windscreen? It's because there's this very thin air layer that actually sits there and it covers and protects the dust on the bonnet. Now, you get an outdoor airfoam on top of your roof too. That actually has a resistance of 0.03. Metal cladding has no resistance at all. It's a good conductor of heat and the absence of heat, so it has a resistance of 0. There's a roof airspace. If you have 50 to 100, 50 millimeters to 100 millimeters, non-reflective, you have a resistance of 0.16. If you apply a plasterboard that is 10 millimeters thick, there's a resistance of 0.06. The same applies to the outside. You actually have an indoor airfoam, still air. That's air that doesn't move. This air can actually move along the material. So we have 0.11 for our indoor airfoam. That gives us a total R value of 0.36. This is what I meant that other materials make up a R value count, which is the same as what that is. Now we have the remaining amount from 3.7 to 0.36. We still have a resistance that we need to achieve of 3.34. What material will we choose to give us a minimum for that amount? Right, so if I had to choose, say for example, EPX, I need a 95 millimeter thickness board to allow for a 3.34 R value with a total of 0.36, 3.34, to give me a 3.7. I can change this. I can use a rigid board. I only need 85 thick. EPS, I need 120 thick. So the choice is yours in design application when you do retrofitting what insulation board you want to use. But remember, if you decide to use EPS board, your minimum amount has to be 120 millimeters.